Hi everyone, today I'm going to be talking about free radical substitution reactions. A radical substitution reaction is a substitution reaction involving free radicals as reactive intermediates. This process will always involve at least two steps and a possible third one. So the first step of the reaction is called initiation, and this is where a free radical is created via homolysis. Homolysis is where each of the fragments retains one of the originally bonded electrons, and homolysis usually occurs with the presence of UV light or heat, which will be shown under your reaction arrow. So as you can see here, we have Cl2 going through the initiation process, and it is resulting in two free radical chlorine molecules. And just so we remember that when we're going through any mechanism that involves free radicals, we have to use a single-headed arrow as we're showing the movement of one valence electron rather than a double-headed arrow, which demonstrates the movement of two valence electrons like we're used to. The second step, or the second possible step, this is the optional one I had mentioned previously. This step is called propagation, and this happens if the radical group or groups go on to react further instead of terminating the reaction. The steps where new radicals are formed for secondary reactions and can be used throughout and then react is known as propagation. The end product of propagation is a new molecule and a new radical. So, as we can see in this first step, the chlorine radical will attack the methane molecule by breaking one nonpolar CH bond to form HCl, and a methyl radical molecule will form as well as our products. The methyl radical will go on to attack another chlorine molecule, like shown in the second step, creating chloromethane and a new chlorine radical. So this new chlorine radical that we have circled will follow the arrow and can now be used to repeat the step up above. So it is like a domino effect, and you can go through this as many times as you'd like, seeing as your product will always be that chlorine radical and a new molecule. And the final step of the substitution reaction is termination. And in termination, this is where the radical recombines with another radical species to form molecules, and they are removed from the reaction mixture. So as we can see, we have two chlorine radicals that are forming together to have Cl2. We're having CH3 radical and a chlorine radical coming together, and so on and so forth. And these will be extracted from the reaction mixture once you're done with the process. So this first example we have a cyclohexane that is reacting with Cl2 and light in this radical substitution. And we know that there are two hydrogens attached to carbon 1. So the Cl2 is going to go through initiation or homolysis to create our two chlorine radicals. One radical will break the CH bond on carbon 1 to create HCl, and the other chlorine radical is going to substitute or replace that hydrogen, resulting in a chlorocyclohexane. Since we have this cyclohexane and each carbon has two hydrogens attached, you can place the Cl on any of the 6 carbons, and this will result in the same product. So our next example, we're using butane, and in some instances, different products can be formed and we can obtain what are called statistical mixtures. So in butane, there are 6 CH3 hydrogens and there are 4 CH2 hydrogens, which represents our ratio of 3:2. And basically, this ratio reflects the expected pattern if our substitution of hydrogen by chlorine was random. So if we just substituted any of the hydrogens at random with the chlorine, our ratio for which product it will be is a 3:2 ratio. And our final example, while free radical substitution usually takes place with halogen, in the substitution of alkyl groups, chlorine is the most reactive and most unselective. So you can have numerous products when using chlorine in substitution, but if you're using bromine, who produces one major product, it's going to be more selective on which hydrogen it replaces. So, as shown in the major product, it is going to choose the most stable carbon, which is carbon 3 in this case, and that is because carbon 3 is a tertiary carbon. This means that that carbon is attached to 3 other carbons, making it the most stable out of the other carbons present. And finally, if iodine was used, there would be no reaction or product obtained, seeing as it is unreactable when it comes to these substitution reactions. Thanks, guys. I hope you found this helpful.